Hello everyone, today I am going to discuss igraph, which is a powerful library for network analysis and visualization. We have worked on this assignment as a part of network science course at IIT Bhilai. This slide also lists our names. My name is Gautam Haldar and my fellow teammates are Prakhar Garg, Raghav Bodigar and Sugandh Kumar. I also mentioned the respective roll numbers and email IDs. Agenda. This slide provides our uh, this slide provides a roadmap of what we will be covering today. Uh, so we will begin by introducing the field of network science to lay the foundation. Then we will answer the question what is igraph and why it is a go-to tool in this field. After that, we will dive into its feature and advantages, exploring what makes iGraph stand out. We will also compare iGraph versus other tools such as NetworkX and Jiffy to see how it stacks up against alternatives. Following that, we will look at applications and use cases to understand how iGraph is applied in real world problems. Finally, we will close the session with a conclusion summarizing our insights. Introduction to Network Science. In this slide, we introduce network science, which is the study of complex systems, models as graphs. Many real world systems can be modeled this way, whether it's social networks, where individuals are represented as nodes and social relationship as edges. Biological networks such as protein-protein interaction networks. The internet where router and servers act as nodes and connections between them as edges. The key goal of network science is to understand both the structure, how how components are organized and connected, and the dynamics, how the components interact over time. This understanding helps us reveal hidden patterns and optimize processes within the system. Importance of network analysis. This slide focuses on the importance of network analysis, which is practical side of network science. Network analysis enables us to identify influential nodes. For instance, in social media, this could be identifying key influencers who can spread information effectively. In a biological system, it could be identifying critical proteins. Detect communities. Grouping nodes into communities helps us recognize structures like social cliques, modular subnetworks in biological systems, or organizational units in corporate networks. Understand information flow. This refers to understanding how information influence or even disease propagate across networks, helping us design interventions or optimize communication processes. So, what is iGraph? Here we introduce iGraph, which is an open source library specifically designed for analyzing and visualizing complex networks. It is it is versatile and support multiple languages such as Python, R, and C, making it accessible to wide range of users. The library is optimized for large scale networks, meaning it can handle graphs with millions of edges and nodes efficiently. It provides not just analytical tools but also visualization capabilities, which make it a comprehensive solution for network science tasks. History of igraph. igraph was initially developed in 2003 by Gabor Sherdi with a focus on creating a fast and scalable network analyzing tool. Over the years, it has grown in popularity and has been widely adopted in both academic research community and industry. What has set iGraph apart is its commitment to performance, especially when dealing with very large networks, thanks to its efficient implementation in C, while also offering high-level APIs in Python and R. Today, iGraph is considered one of the most mature and reliable tools for network analysis. iGraph features. Some key features of iGraph includes graph creation and manipulation. So you can easily create a graph from scratch or load them from file and then modify them by adding or removing nodes and edges. A comprehensive set of algorithms such as shortest path calculations, clustering, centrality measures, and community detection methods. Support for both directed and undirected graphs, which allows users to model a wide variety of real-world networks depending on whether edge directionality matters. Graph types supported. With iGraph, you can work with several types of graphs to suit different analytical needs, like directed graphs where edges have a direction, like from node A to towards node B, which is useful in modeling things like follower following relationships on Twitter. Then undirected graphs where edges are bidirectional or mutual. Example, friendship network in Facebook. Then weighted graphs where edges carry weights. Example, distance, costs, or strengths of relationships. Then bipartite graphs, which consist of two distinct sets of nodes and edges only run between nodes of opposite sets. This is often used in recommendation systems and matching problems. So then basic graph operations. iGraph allows you to perform all essential graph operations required for analysis. You can add nodes and edges easily using its APIs. Similarly, you can delete nodes and edges, allowing you to prune your graph or dynamically modify it based on certain conditions. Then you can query neighbors, meaning you can quickly find which nodes are directly connected to a given node, and you can also find paths or compute distance between nodes. These fundamental operations form the basis for performing more complex algorithms such as shortest path or centrality calculations. iGraph for network visualization. iGraph is not just for computation, it also comes with built-in tools for network visualization also. It offers various layout algorithms to help position nodes in a visually meaningful way. You may customize node sizes, colors, and edge styles, which is helpful for making the graph more interpretable and aesthetically pleasing. Finally, iGraph allows you to export your visualizations to common formats like PNG, SVG, or PDF, making it convenient for reports, presentation, and publications. Layout algorithms. Layout algorithms in iGraph help determine how the graph will look when visualized. Some popular ones includes Fucherman Reingold, which is a force-directed layout where nodes repel each other while edges act like springs, helping spread out the graph evenly. Then Kamada Kawai, which is also a force-directed algorithm, but it focuses more on preserving graph theoretic distances. Then circle layout, which is which places nodes uniformly around a circle, often used to highlight symmetrical structures. Then tree layout, which is used for hierarchical networks, especially useful in visualizing organizational structure or phylogenetic trees. So performance efficiency. One of the one of iGraph's biggest strengths is its performance efficiency. It has a low memory footprint, which is crucial when working with networks containing millions of nodes and edges. The algorithms are highly optimized and fast thanks to the core implementation in C. Because of this, iGraph is suitable for large scale problems such as analyzing social media graphs or large biological networks where other tools might struggle due to memory or speed limitations. Okay. Advantages. So from this slide, my fellow teammate Prakhar Garg will explain. Over to you, Prakhar.
Hello everyone, I'm Prakhar Garg and I'm going to cover the second part of this presentation on iGraph. As Gautam has already introduced you to network science concepts and core features of iGraph, I will walk you through the advantages of iGraph. Then I compare iGraph with other tools that are already available in market. Then we will explore the real world applications and usages of iGraph. So first one, let's talk about advantages of iGraph. Uh, First, we will take the topic scalability, as scalability is very important to us. Real life networks are very scalable. They have millions of nodes and edges. iGraph can handle this type of network very effectively. Second thing, iGraph provides us speed without compromising memory of the device. So in case of speed and memory, it's also scalable. Like what I mean is, in very vast networks, it will give us analysis and analysis in very short time, and it will not affect the device of that memory. Then thirdly, it is essential for real world problems like social networks and transportation system. Example of social networks we can take as Instagram, Twitter, and all. And transportation networks, like traffic in a city or in a metropolitan area or not that wide area network. So secondly, we will talk about flexibility. So when we talk about flexibility, we will talk about how igraph can be integrated with our projects and systems, and how it can be used in different platforms, as igraph is written in many languages like R, C, and Python. So in backend igraph is written in C, so it is very efficient and very fast because of the C programming language. Now, thirdly, we will ask about speed of igraph. So, as igraph is written in C language, so it is very high performance language. C is very high performance language, and that's why igraph provides analysis very speedily. It processes large network very quickly and efficiently, because it has fast graph algorithms that are integrated already in igraph. Next, we will talk about versatility of igraph. So igraph supports many type of graph types, as Gautam has already told you about types of the graph: directed graph, undirected graph, weighted graph, and bipartite graph. This all are supported by igraph. So we will not go into the definition of it. Then when we talk about versatility, we can also talk about dynamicity of that graph, in which new edges are constantly added and deleted. So in dynamic graphs, igraph is very useful. Uh, s- and the last advantages, we will talk about algorithms that are already integrated in igraph. So these algorithms are mainly used for detecting communities, taking centrality measures, and finding short path clustering. So it helps us cover meaningful pattern in our data, and there are many algorithms which we will discuss later. Now let's talk on the virtual visualization which are provided by igraph. As visualization is the very basic and most important part of igraph, because from which we can take insights directly. So, igraph has built-in tools for visualization networks. They are based on layout algorithms like Fretman Reingold algorithm and Kamada-Kawai algorithms. Uh, so igraphs are basically used in native plotting, and compatible with external tools like Matplotlib. Um, we can export our graph that we have taken from our analysis, and save into formats like PNG and SVG mainly. Um so these are all advantages that we have seen right now. Next up, we want to compare igraph with other tools, network tools. So we will understand in this section how igraph is very much important and better than other uh, networks, and where it lacks, like where it has disadvantage. The first up in igraph, we will compare it with NetworkX, as NetworkX is also a widely known tool for generating graphs of many networks. So, in comparison to Network X, iGraphs is very faster. Networks X is a bit slower than iGraph, and iGraph is optimized for speed uh, versus to Network X. iGraph can also support scalable networks, real life networks like people interaction, and like six node example, like six node interaction of all over the world. So igraph can plot such graphs very efficiently rather than network x. So what network x provide better is network is mainly written is in Python language, and that's why it is widely used by new coders, and it's a great for quick prototyping. Like you can take a sample graph for a vast network and prototype it, so you can make get insights from a very short network. And so versus to that, igraph excels in big data, but for shorter data, network x is better than igraph. Now let's move on to next tool, igraph versus Giphy. Giphy is also a very well-known tool for generating graphs on networks. So Giphy is basically a graphic user interface based tool. So it mainly focuses on getting out the insights which are visually appealing to the end user. So they can be used in businesses and various fancy presentations. So it provides graphs that are very interactive to user and which are very appealing. iGraph is better for scripting the format of your network, which Giphy does not provide that very well. And iGraph is also very good for automation. Uh, Giphy is not good at automation. Like if you are want to iterate your graph multiple times in a continuous time interval, then Giphy will not help you that much. But iGraph will be efficient in that. It has already have integrated algorithms and tools for that. Giphy is suitable for just visualization, and iGraph excels in automation and analysis. That's it. As I want to also tell that if you can say that Giphy is more visually attractive, but insights are always comparable in iGraph and Giphy, so there will be no difference in uh, the analysis insight that you will get at the end. Let's move on to third part of our presentation, uh, which is uh, which is discussion on applications. Then we will go on the fourth part of our application presentation, which is use cases. So when we are talking about applications of the iGraph where we can use it, first let us talk about the most well-known networks, social networks. So social networks, many apps are based on social networks like Twitter, Instagram, X, and all. So, in social networks, iGraphs helps analysis friendship between peoples or friendship between nodes. Then, in if we take example of Instagram, we can analyze that how a single node is connected to multiple followers and how the important nodes collaborate with each other. These are very helpful insights we can get from using iGraph. So in social networks, iGraph can be also used in identifying influencer and analysis communities. So in real world networks, people from communities vary quickly, and as a human is a social animal. So with iGraph, we can easily cluster these communities and detect them. And the main purpose of doing all this for social networks is maintaining and governing and analyzing how information flows in the network, because uh, for social network, information is like a very important weapon that can be used against or in advantage of it. Next up, let's talk about applications in biological networks. So, in biological networks, we have already discussed in our Barabasi book that about protein-protein interaction, in which there is particularly some nodes which have very exponential high degree, and most of the graph is with less degree. Let's talk something more about gene regulatory networks. So when we plot graph from for genes and all, so just a little tweak in a genes uh, can manipulate and generate a new organisms. So analyzing that graphs are very helpful in biological research to uncover molecular relationship between different molecules, how they can connect, and how we can manipulate them to form new molecules. Let's talk about next application of iGraph where we can use it. So we can use in infrastructure networks. So by infrastructure, I mean that the big infrastructure that are needed for uh, men- that are needed for our societies. We have taken two examples in it. First one is power grid, and second one is transportation systems. So power grid, we have known that it connects all the places. It also connects places where there are less humans. So uh, how iGraph helps in these examples is that with iGraph we can get insights like traffic flow, or electricity distribution, and predict system failures. So in power grid system, if a node fails, that with iGraph we can generally plot that if a cluster is affected by power failure, so we can easily reduce that. The failure cause can be caused by an important node that is connection between power grid system and the affected area. So that's how we can point out the system failures. Next up, we are going to discuss about another application, which is information diffusion. As we have already seen in Corona, and we also see in day-to-day life in Twitter, like information is diffused very quickly in a social network, but it's affected by the importance of a node. If not very important node try to diffuse an idea, it will not spread very easily and very exponentially. But if an important node does the same thing, it affects the network very quickly, and the information diffuses very quickly because of that. So how it actually happens, like uh, we we have taken this point just because it is applied in epidemic models, and understanding the information spread and disease spread in such models, it will give us idea how some things can spread very quickly and in which part of the network. Let's us move on to another part of this last part of this presentation, which are use cases. The first one we have taken use cases example. First is community detection. So community detection is a very important part in every social network. People form communities very easily, and they are prone to form communities. Algorithms like fast greedy that are already integrated in this Jaden iGraph. Another algorithm is Loevian algorithm, which this both algorithm helps us detect communities within a network with very efficiency. Now iGraph also reveals groups of closely connected nodes, which we call community, and useful for social networks and biological systems. So, community detection in biological system is also very important, as some molecules from clusters very heavily and and attracts so many free nodes. So we can understand that if a node is causing that, if it's important or it's a virus or it's anything that causing this. So that's how we community detection is very important, and igraphs helps us with it for from its inbuilt tools and all. So another use cases, and the last use case we have taken is centrality analysis. Centrality analysis is very important, and we have taken three key points to refer to. So these three points, like degree centrality, betweenness centrality, and eigenvector centrality, are very important. Degree centrality is basically measures the number of direct connection a node has, and betweenness centrality identifies node that controls information flow. What we mean is, in a betweenness centrality, if a node is between very it has all the sites are covered with most of the nodes, then that node, the central node, become very important because it is in between of many nodes, and it governs the information flow in other parts of the network. So between the centrality gives us and tells us about more about the importance of that node. On the other hand, eigenvector centrality only finds nodes connected to other important nodes in a network. So eigenvector node gives us the secondary importance from the primary ones, and it is also a very important centrality measure. Let us conclude our four parts of the iGraphs, and let's summarize all this and what we have gained from the this presentation. So we can say that iGraph is not best in visualization, and not the best in uh, making small prototypes. So for that we have other tools too, but what igraph provides, which is very important, is first one, igraph provides a very lightweight analysis, and it's very fast. Igraph is very optimized for performance only, and it provides analysis with accuracy, but with very fast speed, even on very large data set with millions of nodes and edges. Second, iGraph is a robust graph algorithms. It has robust graph integrated algorithms, which provide powerful tools for, as we have seen, community detection, centrality analysis, and much more. Last one, it is very flexible and scalable. It handles networks of all sizes from small to massive, and is adaptable to different programming languages. So everyone can use it, and it's mainly used by researchers and students. We have used igraph for our projects. uh, Let us end this presentation with the conclusion. So, as we have seen that even if iGraph is not very interactive and providing very graphical results and fancy results, but it's a very useful tool and a very optimized tool for research work and network analysis. So it is a perfectly best tool for large scale graph for analysis. And it whether you are working on a social network, biological network, or infrastructure type of networks, uh, this igraph tool is ideal for all this real world application. And let us conclude with the only 3 points which are mainly provided by igraph. Which are speed, scalability, and rich algorithm integrated in igraph. So this is my part. Next, thank you all, and Sugandha and Raghav uh, will will explain on the hands-on demonstration of the igraph. And let's hand over to Sugandha and Raghav.
Hi everyone, my name is Sugan Kumar. So today we will do hands-on on iGraph, a powerful Python library for network analysis and visualization. As we know, networks are everywhere, like social media, roadmap, biological system, and even recommendation algorithm rely on a network structure. So iGraph allow us to create, analyze, and visualize this network efficiently. So through this session, we will install and set up iGraph. Second, we will do create and modify graph. Third, we will visualize network structure, and we will also perform key uh, uh, graph-based computation and many more. So let's begin with installation and environmental setup. So to use iGraph, we have to install via pip installed Python iGraph using this command. So this command install a Python iGraph package, which is the Python interface for the highly optimized iGraph C library. And second, we also have to install Cairo for enhanced plotting. So Cairo is a graphics library that helps iGraph render better visualization. So to install it, we have to use pip install pycairo. So without Cairo, some visualization function might not work properly. And to verify the installation, we have to run these commands. So if this run without error and print the version name, then the installation is successful. So now we are going to start creating and visualizing networks. So let's start with graph creation and basic manipulation. So a graph can be created in several ways. So let's explore them. So firstly, we are creating empty graph, and then we will do manual addition on the top of that. So creating an empty undirected graph. So with the help of graph function, we will create an empty graph. And with the help of add vertex function, we will add a node to the graph. So here we are choosing 6 vertex and labeled with, by default it is labeled with 0 to 5. And with the help of add edge function, uh, which define the connections between the nodes, and with the help of summary function, it brings the basic graph details. So now move to the creating a graph from edge list. So with the help of graph function, again we have to pass edge equal to edges and direct equal to false. It creates a graph from the edge list, and with the help of these commands, we are assigning custom labels to the vertex, and it is useful when working with a real world data set. Now create graph with adjacency matrix. So adjacency matrix is a square matrix used to represent a graph. So each row and column represent a graph, represent a node in the graph, and the value inside the matrix indicates whether two nodes are connected or not. So 1 indicate there is an edge between the two nodes, and 0 indicate there is no connection exist between the nodes. So this method is useful for the large network. Now I will explain like what this line of code means. So if a greater than 0 indicates convert a matrix A into the Boolean matrix, where true means there is an edge and false means there is no edge. And with the help of two list function, we are converting the numpy array into the Python list. And with the help of graph adjacency function, we are creating a graph uh, based on adjacency matrix. And if true, an edge is created between the respective nodes. Now we are assigning uh, labels with the help of these line of codes. By default, it is labeled with 0, 1, but we can assign as per the use cases. And with the help of summary, we provide a quick overview of the graph, like number of node we have in the graph, number of connections we have in the graph, and whether it is directed or undirected. So now we will do graph modification functionality, that will be adding and removing vertex and edges. So firstly, we will see adding a vertex with a custom attribute. So with the help of these functions, add vertex, it means like we are adding a new vertex named grace to the graph, and every node in iGraph can have attributes such as a name, color, or weight. So here we set a name attributes for the new vertex, and with the help of this command, we are retrieving the list of names of all vertex. So the graph now has new vertex called grace, and the previously existing vertex remain unchanged. So now with the help of these line of commands, we are adding an edge between the new vertex and an existing one. So we are creating an edge between vertex 6, that is grace, and vertex 0, that is label a vertex. So, and with the help uh, of this command, uh, we are retrieving a list of all edges in the graph, and original edges remain unchanged. So with the help of these commands, we are removing an edge uh, between two existing nodes. So for that, we have to find an edge ID with the help of get ID. So as we are passing 1 and 3, it will find the HIT of the connections between vertex 1 and vertex 3. And with the help of uh, delete edges, we will delete the edge identified by a index. So, and with the help of this get list command, get edge list command, we are retrieving the list of edges after deletion. So now the edge 1 comma 3 was removed and the rest of the graph remain unchanged. And why is this important? Because adding vertex dynamically allow the graph to grow in the real time. Adding edge helps define relationship between nodes, and deleting edge allow us to modify network based on the new information. Uh, Now let's update the graph attribute. So with the help of these commands, we are storing colors value for each node, and with the help of uh, these commands, uh, we are storing edge leads. Next here. Now we will see the advanced analysis functions like centrality and connectivity. So these sections of code computes three important graph metrics that helps in analyzing the structure of a network. So degree centrality measures the number of connections a vertex has between the centrality identify key nodes that act as a bridge. Closeness centrality measures how close a node is to with all other nodes. And as we see the output, vertex ABCE has degree 2, means connected to two vertex, and vertex D and F has degree 1, means uh, only connected to one vertex. Now moving to between the centrality, it measures how often a node lies on the shortest path between other nodes. So higher betweenness means the node is critical bridge in the network. So as we see the output, vertex E has the highest betweenness, that is 1. It means many shortest path passes through it, and node F has betweenness 0 since it is a end node and no path go through it. Talking about closest centrality, it measures how easily a node can reach all the others. So as we see the output, ABC has the highest closeness. This means it will reaches all nodes quickly, and vertex D and F has the lowest closeness. This means it is far from most node. So summary of the sections is like compute degree means number of connections each node has. Compute betweenness means how often a node act as a bridge. Compute closeness means how easily a node can reach others. And why is this important? Degree helps to find the most connected node. Betweenness helps to identify important intermediates. And closeness helps to show efficiency uh, reachable nodes. Now let's move to the eigenvalue centrality. It measures of influence in the network, unlike degree centrality, which counts direct connection. Eigenvector centrality also consider the importance of a node neighbors. In simple term, a node is more important if it is connected to other important node. This concept is used in Google page ranker algorithm, which ranks web pages. So with the help of uh, this command, we are calculating eigenvalue centrality for each vertex, and it will returns a list of value where higher value indicates more influential nodes. So as we see the output, vertex A has highest eigenvalue singularity. It means it is connected to higher connected node, and the vertex F has the lowest. It is less. It means it is less connected and isolated. So let's move to the graph connectivity in component. So these sections of code helps analyzing how the graph is structured by identifying connected components and check if the graph is fully connected or not. So a connected component is a subgraph where every vertex is reachable from every other vertex within the component. So if two nodes are not connected by any path, they belong to different component. So with the help of uh, these commands, uh, we are finding all group of connected nodes, and with the help of this command length, it tells how many separated component exist. As we are getting as we see this output, it means the graph has two disconnected group, uh, and it forms two disconnected groups in which a vertex AB have formed one group and CD have formed another. And with the help of these commands, uh, actually it returns true or false. If all the nodes are reachable, then it will return true, and it will return false. The graph is split into multiple disconnected parts. So summary of these sections is like connected component functions find all the disconnected subgraph, and is connected function checks if all nodes are reachable or not. So let's move to the clustering coefficient and transitivity matrix. It measures how tightly connected uh, a network is. So clustering coefficient measures the likelihood that two neighbors of a nodes are connected. So higher value means a more tightly network. It is calculated for each node and then average. With the help of uh, this command, actually this function returns computes the local clustering coefficient for all nodes and mod equal to 0, and so nodes with degree less than 2 get 0 instead of NAM value. So if 0 network has local triangle, if 1, all possible triangles are fully formed. So let's move to the global transitivity. It measures the overall tendency of a network to form triangles, and it is also called global clustering coefficient. So with the help of these functions, it computes the global transitivity for a undirected graph, and it gives a single value for the entire network. So higher transitivity means more interconnected network, and lower transitivity suggests fewer triangles. So summary of this section is like average clustering coefficient measures how tightly nodes form local triangles. Global transitivity measures the overall triangle density in the network. Higher value means a more interconnected network. Now let's move to the shortest path and the distance. So this section of code calculates the shortest path and the diameter of a graph, and both are crucial for understanding network efficiency. So the shortest path between two nodes is the minimum number of edges needed to travel from one node to another. So with the help of g dot distance functions, it computes the shortest path from vertex 0 to all other vertex because we are passing 0. So that's why it will calculate shortest, shortest path from 0 to all other vertex. And it returns a matrix where each entry represents the distance from vertex 0 to other node as we see the output. So let's move to the diameter of a graph. So the diameter is the longest shortest path in the graph. It represents how far apart the two most distinct nodes are. So lower diameter indicates the network is more efficient. Higher diameter, some nodes are very far apart. So with the help of g dot diameter function, it finds the largest shortest path in the graph and it returns an integer value represent the longest shortest distance. So summary of this sections is like shortest path measure how quickly nodes are reachable, and graph diameter finds the farthest distance between any two nodes. Now let's move to the community detection and advanced clustering concepts. So community detection help identify groups of a node that are more closely connected within the network. There are several ways to detect community. First one is walk trap. So walk trap uh, is based on random walk. So the idea is that short random walk tends to stay within the same community. So as we see the code, so g dot community walk trap function runs the walk trap algorithm, and this function as clustering function converts the result into actual communities. As output, we will get a list of community where each community contains nodes or that are strongly connected. Second, we will see another method that is multi-level method. This method detect community at different level, starting with small group and merging them into larger ones. So the goal is to maximize modularity, meaning community that having strong internal connection but weak external links. As we will see the code, so g dot community multi-level runs the community detection algorithm, and out it will give an output a list of communities. Uh, and the third one is to detect the community is label propagation. So a simple and the fastest method for community detection. So each node start with unique label and label is spread through the network until community is formed. And the algorithm run until label stop change. As we see the code, so g dot community label propagation, it runs the label propagation algorithm, and let's see the output. So it represents every community detection algorithm group. The graph has six nodes, and algorithm every algorithm has detected two communities. That is also known as clusters. So and the nodes inside each community are not explicitly listed. So summary of these sections of this code are each algorithm found two groups but may have assigned node differently. Output only show cluster counts, but we can retrieve the actual node group by printing them properly. Now move to the visualization of community. So this section of code assigned colors to detect communities and plot the graph to visualize how nodes are grouped. So with the help of coloring palette function, it creates a color palette uh, with as many colors as there are communities. So if there are three communities, it will generate three different color. And palette dot get many So this function assign a unique color to each node based on its community. So and uh, g dot vs equal to colors assign these color to the vertex. So this allow each community to visually distinct. And what is as you see this here we see there is an FR. So what is FR? It position nodes so that connected nodes stay closer together, and nodes with more edges move towards the center. As now I will tell you about what these line means. Uh, so these lines indicate the set of size of each node, and this line will display the node needs having A, B, C, and uh, this line uses the FR layout for positioning. And with the help of these line, it shows the size of plot. Here we are using 500 cross 500 pixels, and with the help of this line, we are adding space around the graph. And with the help of IZ plot, we plot the graph with the assigned color and layout, and each community appears in different color. As we see the expected output, nodes group with two distinct color, and there is a strong internal connection within the communities. So now my friend Rafa will explain the remaining part.
Hey guys, this is Raghav, and in this section of the tutorial, we are going to talk about graph simulation and synthetic networks. But before that, let's have a quick recap of what we have studied till now. So, we got to know how to install igraph using pip, and how to create simple graphs, adding nodes, removing them, adding edges, removing, and creating graph using different methods, be it adjacency list or be it a matrix. Then we saw some centrality measures such as degree centrality, betweenness centrality, eigenvector centrality, all these things. Then we went towards community detection. We tried to identify different communities. And finally, we came to the visualization where we visualized this specific graph. Now, I want all of you to please remember this particular style, this particular graph, because later on, I am going to reintroduce this for some other task. Okay. So let's come to graph simulation and synthetic networks. So the first thing is, as it is written here, that generating random graphs. Okay. So as we are aware, graphs are consist of two things: nodes and the edges. Okay. And if we say that the way they are connected follow some kind of a distribution, or probabilistically, if we are able to determine how these nodes are going to be connected by those edges, we can generate random graphs. Okay. So there are different methods, different approaches given by different graph scientists, I should say, who have uh, made significant contributions to this field. So let's discuss the first one, that is Erdos-Renyi random graph. Okay, so some key features is, first one is randomness. It is self-explanatory. I don't think I need to explain it. What happens is that each pair of nodes is connected with a probability p. Okay, so each link being present in the graph has a probability p. It may be present, it may be not. It depends on its probability. And the degree distribution of the nodes follows a binomial distribution, as it is written here. If the number of edges are small or fixed, and if the graph is growing, or I should say the graph is really large, then that condenses to follow Poisson distribution. Okay, then once again, it is very easily applied to homogeneous graphs. Okay, in contrast to other scale theory networks such as Barabasi Elbert, the Erdos-Renyi model generates homogeneous graphs. Okay, so this is one feature of Erdos-Renyi, where all the nodes which we have in our graph are treated as same kind of entities. Okay, now some properties of Erdos-Renyi model. First, as I mentioned earlier, that the degree of nodes follow a binomial distribution, where average degree is given by p into n minus 1. So this is a mathematical expression for uh, the average degree. Okay, then This means that all nodes in an Erdős-Rényi graph are likely to have a degree close to average, with no nodes having a degree much higher than others. So what it actually means is that once again it follows a binomial distribution. Percolation and phase transition. See, as the edge probability p increases, what is going to happen? Earlier, for small values of p, there are going to be disconnected components. Now, as the value of p increases, we are going to see the emergence of one giant component, one large subgraph. Okay, so this is another feature. Then we have small average path length. So what is why are we talking about average path length here? Because uh, as most of the edges are going to be, if you have seen a binomial distribution, it is centered around the mean. Okay, so most of the edges are going to have uh, the average number of nodes. So what happens in this is the path, or I should say the ease of travel from one node to any other node uh, is there, which is missing in some other approaches. Okay, so similar to Barabasi-Albert model, Erdős-Rényi graph exhibit a small world property. What it means is average number of steps to travel between any two nodes grows logarithmically with the number of nodes. Okay, so definitely if it is if we draw a line y is equals to x, and if any curve is going below that, we say that it is slow moving or slowly growing, and if it is above that, we say that it is quickly growing. So in this case, it grows very slowly. Another thing is the robustness to random failures and vulnerability to targeted attacks. Erdős-Rényi graph is quite robust to random failures. Once again, we know the reason, as uh, the degree is not concentrated on one particular node. Okay, there are many nodes which share at least the average degree. Okay, so removing a particular random node or the edge is not going to affect the network significantly. However, the network is vulnerable to targeted attacks. Okay, so let's say if a significant number of high degree nodes are removed, it may break apart quickly. Okay, then applications of Erdős-Rényi models are usually seen in basic network models, which are used to teach network science. Then computer networks, sometimes topologies and all these things, we can consider them as an application or examples of Erdős-Rényi model. Similarly, in epidemiology as well, we see such examples. Now, let's come to plotting it. Okay, so as you can see, using iGraph, it is quite easy to plot an Erdős-Rényi model, and there are two parameters which it takes. The first one is the number of nodes, that is n, and the second one is the probability p, that is the probability of any link being presented between any pair of these 20 nodes. Okay, then once again, we are providing some names to it. Okay, so let's say vertex 1, vertex 2, all till vertex 19. We are beginning from 0, that's why, and we are giving some layout. Now what exactly does this layout mean, I'll tell you later. Okay, for now just assume that there is something called layout which is used when we plot it. Okay, under the simple function ig.plot, what it does, we pass a graph to it, a layout, vertex label if we want to, this is not compulsory, vertex colors, and bbox. So what is bbox? Bbox is the size of this image that we are receiving here. Okay, so an interesting thing is when I run this, what you'll see, each time the layout changes a bit. Okay, every time you will see that the layout changes. Okay, because it is following the Erdős-Rényi model approximately. Okay, so sometimes you may see that there are a few disconnected nodes as well. Sometimes there are over connected nodes, okay, which are connected to so many other nodes. Okay, so this is how we plot simple Erdős-Rényi graphs using iGraph. The second kind of graph, which happens to be my favorite, is the Barabasi-Albert scale-free graph. So earlier, what we saw, that Erdős-Rényi graph was and its nodes were following a degree distribution identical to binomial one. Now, in this case, it is different. Here, the node degrees follow power law degree distribution. Okay, so power law distribution, which is mathematically given by this formula. Okay, so there is a probability p of k of a node having k degrees. Okay, so the probability of a node having k degrees is given by p of k, which is somewhat proportional to k to the power minus gamma. The value of gamma is typically taken between 2 and 3, and this is actually norm. Okay, so this is not in my hands. So but this is also a defining characteristic. Okay, defining characteristic, and why we are saying that it is defining characteristic, because it is the only hyperparameter which we change and it results in different kinds of graphs being plotted. Now, once again, even this particular approach, Barabasi-Albert approach, has an advantage of having small average path length. Okay, so once again, average path length is small, and a particular reason for that can be attributed to power law degree distribution. Why? Because there are a few nodes which we can call the central nodes. Okay, because when power law distribution is followed, it is I should say like a uh, hyperbolic distribution. Okay, so like one by x is plotted, something like that. Okay, so in this case, what exactly happens is there may be a node which is a central node and other nodes are situated around it, and that node actually helps to reduce the average path length. Okay, because it is connected to so many other nodes that it basically becomes a center of movement in case we have to move from one node to the other. uh, a presence of hubs, this is another feature. Presence of hubs have are there. First of all, there is a presence of hubs, and they have extremely high degrees as compared to the other ones. Okay, and these hubs, as I earlier told you, these hubs play a central role in networks connectivity. Okay, this is in contrast to random networks where it is much more uniform. Once again, this is robust to random failures and vulnerability to targeted attacks. Now, scale-free networks are robust to random failures. Okay, the reason behind it is if we are removing a random node, there is a high probability that a node with relatively low degree will be removed, which will leave the network largely intact. But if there is a targeted attack and if a high degree node is removed, the network uh, simply breaks apart. Okay, or I should say disconnects rapidly, or I should say that if an attack is made on a high degree node, the network becomes brittle. Okay, so some applications of Barabasi Albert are social networks such as Facebook or Twitter, where we are see that a few number of nodes, or I should say people, have millions, hundreds of millions of followers, while some others like me struggle to get even hundreds of them. Okay, so internet is one again an application where sites like Google and YouTube take up most of the traffic that is passing through the internet, while some other websites struggle to get that much. Once again, we are following a similar approach to plot it. In this case, earlier where we are taking probability, here we are taking m. And what exactly is this m? This is the gamma parameter. So while passing for creating it, the function is ig.graph.barabasi, and the two parameters which are needed as first is the number of nodes and second is m. Okay. So while plotting it, what does it represents that each time when a new node is added, two edges originate from it. Okay, and the concept that is followed here is what we call preferable attachment. Okay, so once again, let's plot it. Now let's try to change the value. Let's plot it for 50, and we'll also make it bigger so that it is easily visible. Yeah, as you can see here, we have increased. I think I should change this as well. 50. Yeah. Now, as you can see here, there are a few central nodes which have a very high degree, and then as we go beyond that, we are seeing that most of them are either stuck at one or usually 1 or 2 degrees. As we see, this has two, 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 two. So the most of the nodes have 2 degrees, while there are a few central ones such as V0 and V1 which have quite a lot connections. Okay, so this is a good display of Barabasi-Albert model graph. Then the third is Schwarz-Strogatz or a small world graph. Okay, this is not exactly my favorite, but yeah, it does exhibit a small world property. So what is this? Once again, what is a small world property? It means that though there are a large number of nodes, average path length is very small. Okay, and most of the nodes can be reached from any other node by traversing only a few edges. A distinct characteristic for this particular model is high clustering coefficient. So clustering coefficient, what does it mean? It means that how well uh, a node's particular neighbors are connected with each other, and it helps us identify whether there are any strongly connected components present in our graph. Components can also be referred to as subgraphs. Okay, so what Strogatz model generate graphs which have a high clustering coefficient, which means the nodes are very likely to be connected to each other if they have a shared neighbor. And this property sometimes is also seen in social networks where friends of friends may become friends. Okay, then transition between regular and random networks. See, Watt-Strogat's model generates model that transition from a regular lattice to random network as the rewiring probability increases. Okay, so what exactly happens here is, first we have a model, and then we put some more edges into it, such that its average path length decreases, and it becomes easier to travel from one node to the other. It is I have actually explained it below as well. So transitioning property, how does it work? Uh, to balance between regular and random networks, the rewiring probability P controls the balance. Okay, and how does it control? For P is equals to 0, the network is regular lattice with a high clustering but long average paths, and P is equals to 1, the network is completely random. Okay, which means that the clustering coefficient is low and average path length is very short. Okay, for intermediate values of P, what we see that the network exhibits small world properties, high clustering, and short average path length. Okay, so we can say that this is one of the most wholesome models that we see. Once again, small world, if we talk about its robustness or vulnerability, small world networks, including those generated by Watt-Strogas, are generally robust to random failures. The reason we all know, redundant paths are there, and they ensure that network remains connected. But once again, if targeted attacks are made, they may be vulnerable to them. And this again is a syntax of how to plot a sample Watt-Strogat's graph. Okay, so it takes 4 parameters: dimension, size, NEI, and P. So once again, when we're talking about P, what is P? P is the probability. What is P? P is the probability, and which in this case is 0.1. Okay, so as I told you, if the probability P is less, what we are seeing, comparatively long average path length for P is equals to 1, the network is random with low clustering coefficient and short average path length. Once again, let's try taking a bigger value. Let's take 0.9 and see what does this graph exhibit. See, now in this case, because we have put the layout to circle, we are seeing things like this. But if I change it to R, now see. Okay, so in this case, the it is difficult to comprehend anything. That is why I took the layout as circular. Okay, now, and let's take an intermediate value as well. One second. So what we are seeing here is, in this particular case, the average path length has significantly reduced. I don't think we have to travel more than 2 or 3 hops, okay, to reach the node we want to. So this actually explains how can we plot some samples of synthetic graphs, random and synthetic graphs, using igraph library. Now we come towards importing and analyzing real world data. Okay, so once again, let's say we have a set of nodes and edges, and we want to analyze, we want to plot, or we want to perform some operations on them. So how to perform the operations we have already taken care of. Okay, we have already made a graph and we showed it to you. Now the thing is how to import such graphs, okay, which may be present in some other format. So in this case, let's assume we have a graph in CSV. I'll just show you in a bit. So here we have graph with us, which is named interactions.csv, and these are a set of nodes on one side. Okay, and this is a similar set of nodes on the other side as well, and a particular row tells us that a link is present between this node and the other node. Okay, so uh, there is a link between the nodes which are present in the same row in column A and column B. Okay, now how to import this data and later on visualize it? For that, first of all, we will use a library. Okay, import CSV is quite a popular and much used library by those who work in Python. Now, the first task that we have to do is we have to accumulate the edges and then plot them. Okay, so for that, what we are doing is, first of all, we are opening this file and we are reading it. Now, for each row that our variable reader reads, okay, we will segregate each row into 2 parts: source and target, and we will append the source and target to the edges. Okay, so in this case, how many we have 47. We have around 47 edges there. Okay, so our edges, this list is going to have a total of 47 connections. While plotting it, what we can do is, we can, for to plot it, we can pass a tuple list. Okay, so this is a tuple list function to which we can pass our list which has which has all the edges, and we can choose whether to make it directed or not, and we can also provide a vertex name if it is there. Okay, if we want to uh, assign some names, we can pass it, otherwise there is no such compulsion. And then to plot it, once again, the simple plot function which we used earlier, the same function I am going to use it again. Okay, and once again, my favorite layout, circular layout, and we are getting this. Now if I want to make it directed, even that can be done. See, okay, now in this case, the direction is given by the arrow, where the node from where the arrow is originating is a source, and where it terminates is the sink. Okay, so this is how we can generate both directed and undirected graphs from a given CSV file. Now once we have a graph which we have imported from a CSV file, we have to analyze it. Okay, so simple way of analyzing is by using matplotlib. Okay, so here what we are analyzing, we are analyzing degree distribution. Okay, so we have already imported the graph above, and now I'll simply plot this. So as you can see that we have a degree distribution here. Okay, so any guesses what kind of degree distribution is it following? Yeah, no points for guessing, but it looks like it is a Poisson distribution. Okay, so as you can see, first the frequency increases and then it decreases. Okay, so yeah, we can say that it is actually mimicking Poisson distribution. Now we can calculate some easy network metrics which are given by average path length and density functions. Okay, which are there in the iGraph itself. Okay, so if I run this, see, so this is the average path length, that is 3.91, and this is the network density, that is 0.05. Okay, so what does it tell us? Average path length, as I like to mention once again, it tells us how many hops are needed on an average to reach from one node to any other target node, while density tells us the number of links present divided by the total number of possible links. Okay, that can be there in a particular network. Now let's talk about some cosmetics. Okay, we already know that we can visualize, but can we make our visualizations better? Okay, and how to do it? So let's talk about some cosmetics, that is visualization enhancements and exporting. Earlier I told you to remember this particular graph. Okay, this is a simple graph where we have two different components. Okay, and now we are going to discuss how to look our graphs, how to make our graphs look nicer. So iGraph offers us a lot of layouts using which we can visualize our graphs. Okay, one such example, as we have already seen above, is the circular layout. But apart from that, there are a few others such as Fructum and Rheingold and Kamada Kawai. Okay, and these are represented by their initials. So we have FR and KK. Okay, so if we want to plot a particular graph in a particular kind of layout, we can simply generate such layouts and then apply them. Okay, so we already have our sample graph G which we had created earlier. Now see, if I apply layout FR, that is Fructum and Rheingold, I will get this kind of a distribution. This kind of a representation of the entire graph. And this in case if I am using Kamada KY, once again this kind. Okay, so and yeah, if I could have used circular, then I would have got something like this. Okay, so it depends on the graph. It actually depends on the graph that what kind of a layout suits it. Okay, usually when we are visualizing small world graphs, we try to visualize it using such circular measures. Okay, but it's up to you. It's totally up to you what kind of layout you prefer. As I already mentioned, this is simply the cosmetics part of iGraph. Okay. Now, what more customizations can we add? We can add, uh, we can change the size of the degree, okay, or edge width, layout. I've already talked about. The size of the graph, or the size, I should say, the size of the visual which we are plotting. Okay, so I'll show you in a second what more we can do. So we are taking this same graph, okay, which we have with us, the same graph, okay, and now what we are going to do, I'm going to change its size such that the uh, the size of nodes become very small. Okay, so here the base size is 2, and then depending on the degree it will increase by a factor of 2. Okay, see. Okay, so what are we seeing here actually, that the sizes have decreased. Okay, now let's make it bigger once again, but this time, yeah, here, can you notice something different? I'll tell you that this particular node, as they have a degree 1, they the size of these nodes is comparatively smaller than the other node, that is this, because it has a higher degree. Okay, so this is another good way to represent a graph where the size of the nodes is dependent on the degree. Another thing is which I can change is edge width. See, so as I change this parameter, particular parameter here, what are we seeing here is the edge width has increased. Now this edge width can also be made proportional to the weight of the edge. Okay, even that is possible. Okay, vertex, similarly, vertex color can also be changed. Vertex label, if it is available, it can also be changed. The size of the visual, which I've already discussed. Let's say if I feel that this size of the visual is too big for only 6 nodes, then I can reduce it, and this is what we get. Okay, so yeah, depending on the size and shape or the layout which we are using, you can change it. Okay, once again I'll bring it to its right dimension so that it is at least visible to all of you. Yeah, now we are approaching towards the end of this tutorial, where once we have drawn the visual, we have plotted the visual which we wanted to, now we want to export it. Okay, so while exporting it, the function is quite simple, ig.plot, once again using a particular visual style that we want to use, and setting a target. So what is this target? This target is actually a path where we want our image to be saved. Okay, so the image can be saved either in the PNG format or in the PDF as well. So if I run this, so once again we have got an image, a plot with thicker edge sizes, and if I open it, you can see here that final graph has been created. If I open it, yeah, okay, and as you can see here, the size that we had mentioned, the size of the image, the size of the plot, 500 by 500, it is exactly that. Okay, so now it's time for some discussion. It's actually some questions for you guys, that you can try to explain why synthetic graphs are useful for testing algorithms and demonstrating network properties, and highlighting how different parameters affect the structure. Okay, so this is a discussion which you can perform within your friends. Now, this is actually the F section is actually the real world network simulation is an extension, or you can say a kind of an appendix section uh, to which we have arrived now. Now, let's talk about it. So, by now we have imported a graph, we have created our own graph. Now, let's talk about what if we have a built-in dataset available. So, yes, iGraph has this capability. It has some built-in datasets. Okay, and to access them, it's quite easy. You just have to add dot famous to the ig dot graph syntax and just mention a name. And here, what we are using is Zachary's Karate Club. Now, Zachary's Karate Club is one of the most prevalent datasets on which the different algorithms are tested. Okay, so what we have done here is we have taken this Zachary's Karate Club graph dataset, and once again we are assigning the labels to all these nodes. We are using a particular layout fr. Once again, if I want, I can change it to circle. Yeah, and as you can see, this is what we get. Okay, so I'll just elaborate a bit on what exactly this data set means. So Zachary's Karate Club is actually a karate club which was based in US, and a study was conducted that during the classes, most of them, the 34 people that attend the karate club, they interact with each other. But what about the time when they step out of the club? After stepping out, do they interact with each other or not? And based on those out of club interactions, this Zachary's Karate Club graph was created. Okay, and though I've not currently shown it here, but uh, it is one of the easiest graph on which we can identify different communities. Okay, so that underlines the importance of this Zachary's Karate Club. Okay, so there are many other famous data sets which you can explore uh, from the iGraph inbuilt datasets. Okay, so you can simply visit this website. It is the signature website of iGraph, and here by some exploration you can definitely find some inbuilt datasets which are there. So once again, we can similarly import real world networks just as we imported our interactions one. Okay, so I'll just go back here. Okay, so similarly, using the same syntax, we can also import some real world networks as well. Okay, and using once again the same syntax, we can plot it. So here I have not done it again. I've simply used the same interactions.csv file to do it. Okay, and this brings to our second discussion. Okay, such data. How can we use such kind of data to model social networks, citation networks, or biological networks? Okay, so as we have already mentioned that some synthetic uh, networks, such as here, applications of Barabasi-Albert model can be seen in biological networks and social networks as well. But you can discuss that how exactly uh, and how well can these models represent social networks or biological networks. Another important discussion can be how does cleaning of data and setting proper attributes before analysis help the analysis? Okay, so this is another topic of discussion on which the class can be conducted. The last part is advantages, limitations, and the best practices. Okay, so yeah, definitely every tutorial, every software, everything in this world has its own some advantages, limitations, and best practices. So I'll just talk about it in a minute or so. So yeah, iGraph, uh, because it uses C language, some fast framework to some extent, it is definitely a faster library. It is flexible. It supports various types of graphs and extensive algorithms. It has visualization support as well. And once again, because it is simply a library, it can be integrated very well with Python. Okay, yeah, so it is very easy to import it just like NumPy, Pandas, or Matplotlib. Okay, the limitations. But yeah, iGraph does come with its limitations. First is the learning curve. Okay, you cannot use iGraph just like you use NumPy. First, you need to have some knowledge of graph theory or network science before you can jump on to hands-on approach and uh, experiment with the various kinds of networks or graphs. Second is visualization complexity. What I personally believe is advanced visualizations or to create such visualizations, you may require some additional libraries, okay, such as Cairo or something. Uh, iGraph in itself is not enough. It A parallel can be drawn where normal data visualization takes place using Matplotlib, but in case if we have to plot some interactive visuals, then we use Plotly. So in here also, if we need some advanced visualizations, we may need Cairo or something. And once again, documentation variability. There are some functionalities which are actually less documented. Yeah. So what is the best practices to learn it? You have to start with small graphs and always and annotate your graphs. Okay. Vertex and edges always need to be annotated so that it can be easily identified that what kind of edges have higher degree, low degree, or any uh, correct measure which can explain it properly. Then we can experiment with different layouts. As why? Because different algorithms, or I should say different kinds of graphs, when represented in different layouts, can reveal some different structural insights. And once again, always remember to cross validate your results. Means use multiple metrics to confirm whatever findings that you have got. Okay, so with this we conclude with our iGraph tutorial. I hope that I haven't bored you, and you definitely learned something from it. With this, saying goodbye to you all guys. All the best towards learning iGraph and other graph softwares, and of course the subject of network science